Okay, so the right side is to choose the time.
Yes.
And the lower side is to choose the wavelengths.
Yes. Yes.
So the ultrafast that is pulse contains many wavelengths.
Yes.
And
yeah, because
so it's somehow it's like a time frequency domain graphic, because wavelengths can be transferred to.
Yeah, you can do that.
So has anyone from your labs did the reverse or inverse wavelet transform?
No.
Like, because it's really close to after the wavelet transform, it can work. It's a time frequency domain.
Yeah, we don't do that in this one. We do it later. You will have talk from beta to the electronic spectroscopy. So we don't have this one. In infrared we did 2D. In that case we are using indeed the frequency domain. In that case we have this pattern on the diagonal, whatever. You can look in which vibrational modes are connected, whatever. In this case it's not needed. Very long time ago we did Fourier transform on this one, but basically this is enough for our purposes, because what I didn't mention that the flavin, they have a very typical absorption in different redox states. And basically what we can follow here, in which redox state is the flavin. And that's why we need wavelengths, because we are following what peaks appear and disappear from the spectra. Because in this case we can assign what happened to the redox state of the flavin. And what I also didn't mention too much, but what you can see here, this is the so-called ground state bleach. This is just to the S0, S1 transition. This is on the left side. You can see the S0, S1 transition. Here, this is the excited state absorption, because these species can absorb some light, and this is excited state absorption. And this one is called the stimulated emission, because it happens that your probe beam can stimulate a part of the population. That's why you have again more light than at the beginning. So this is the typical absorption spectrum. Okay, another question if you have. It was very long, I understand, and maybe too much for such a late hour. Yes.
Yeah. Could you repeat once more about the use of the delay state and the measurement?
Yeah, sure. The thing is that what we are measuring, so this is the delay stage, this is your beam, and this is the delay stage coming. Basically, this is a mirror, and your beam is coming back from this mirror. What we are controlling with the delay stage, it will be the time difference between your pump probe and your pump pulse and your probe pulse. What you do here, you will set yourself. We know in the beginning when we build a system and we start the system, we know when they will arrive in the very same time, and this is what we are calling time zero. And what we are doing here, that we are moving the delay stage, let's say by 1 millimeter, and from this low, we know that how much time is between the pump pulse and the probe pulse if we moved this delay stage by 1 millimeter. Because 1 micron is 3.3 femtoseconds, this means that this will be 3 picoseconds. So the use of the delay stage, basically, this is how we measure time. So we are measuring time not as in the time correlated single photon counting, that we start the measurement, and when the first photon arrives, we stop the measurement. This is how we measure time. We are measuring inversely. We set to a certain distance our delay stage, and we know that 1 millimeter stands for 3 picoseconds. And we will measure what kind of spectrum we will have at 3 picoseconds. So this is an inverse logic, measuring time.
And the time here is
converting back.
Not a time delay.
This is time delay because delay stage makes the time delay, of course.
Yeah.
When we know where are we at the zero time, we set in the software that is a zero
So
time.
it's the zero there. When it's the zero and also like
Yeah, we know when is the zero. Zero is there. Actually, you can see it.
yes.
And we set the differences between the pump and the probe and the pulse pump. Sorry, with the delay stage, and this is what you are measured here. This is this time difference between your probe and pump. Actually, and this is what I showed you here again because it's quite cool, I would say, because you can see how your light is propagating. And actually, it's a huge story how to do that to compensate for this dispersion, because this means that your pulse is dispersed in frequencies. So your red part of the beam arrives earlier. This is what you can see, and the blue arrives later. And sometimes you want to compress it when you want to make a shorter pulse. And this is what you can see here. This is how we know actually that this is time zero. When we are here. Yeah, when we are here, we know that this is time zero. Then we said, okay, zero, because this is where the pulse arrived. Due to the overlap, we have this coherent noise. This is traveling, and that's it. This is already your real signal. Problem, of course, that you lost your first 4 spectra, actually, and you cannot analyze because that was involved in your noise. The better your resolution, the less you will lose at the beginning due to the overlap.
Can you show again the spectrum in the time zero?
Time zero, yeah. So this is where you arrive. This is arriving. And it's propagating. And so basically you count your time zero, let's say from here, the rule of thumb that when you achieve kind of half of your, from here, from your signal, this is your time zero, and that will be your, it's not already time zero because it's already, I don't know, one or 2 picoseconds already. So,
The time zero is the situation when they are all in the excited state.
they are, yes, but they are already in excited state and the probe pulse arrived.
Yes.
So that's why we have this noise. The problem is that we don't have a proper signal because also it's involved or convoluted with the noise. So that's why we always lose a little bit at the beginning, and we can, with the software, we can use a sort of deconvolution when we can subtract this noise from the data set.
And the noise is good from is because of the pulse in the beginning.
Yeah, the noise is, because this is so-called coherent noise, and this is very complicated to explain. Everybody has different explanation. But basically, when in time and in space, the probe and the pulse, probe and the pump arrives, you will have always this coherent noise. The only thing that if you have a short laser pulse, your coherent noise will be shorter, doesn't propagate so long time, actually. But you will always have this one.
And this means that when you do this, when you did this experiment, you move the delay stage like nearly 900 times.
Yep. Not times, 900 picoseconds.
Oh yes.
This is
Yes.
Is it possible maybe that probe beam, except that it probes the molecule, also induces some changes inside of it, some additional excitation or something like that?
yes.
Yeah.
It's possible, just the energy is much smaller. So for the your excitation means we are using a huge energy. When you are basically in the beginning, later we try to make it properly, but at the beginning we just put a much light. This means that you have too much red in the white light, and that's bad because you don't want that one, and actually it's affecting your CCD as well. So anyway, we are reducing with neutral density filters that part, and 90% goes in the other way. And in the other way, it means that it goes through the BVO, and we are making the second harmonic generation. This will be a blue light. This is what we are using for excitation of the flavin. But also, my PhD student last summer, she made this non-collinear optical experimental amplifier, so we can also use excitation beam as a green or orange, what we need actually. But majority of the cases blue is enough.
So why, as we don't understand why we need to excite it first and then hope to detect it?
Because here we are looking for processes which are due to the excitation. So the flavin attracts electrons from the environment, from the nearby amino acids, due to the excitation actually. This is a general property of the flavins. So if you excite the flavin, first excited state, let's say, it's thirsty for electrons, and it will grab an electron. And that's why you have this process in the protein.
And why is and this is why you are calling this process ultra fast?
Yeah, I'm calling it ultra fast because when the flavin grabs this electron from, let's say, a tryptophan, it happens in some proteins in less than a picosecond. And I would say that this is ultra fast. But depends. If you are a physicist, it's not ultra fast. It's almost steady state because for the guys in that second generation, picosecond is not ultra fast anymore. Okay, if you don't have, yeah, go ahead.
I wonder how did you manage to make the one-shot spectrum that you said, and you avoid the converse.
Conversion.
Conversion, yeah.
What you mean in which case?
Yeah, how did you?
I'm asking the back. In which case you mean that I made this spectrum in up conversion setup or?
Yes, in the up conversion.
In the up conversion, you then have basically a spectrum. What you are measuring the kinetics at a certain wavelength. So what happens in up conversion, and that's the problem with up conversion, you have your crystal. Typically, your crystal is, of course, it's a BVO. And let's say your crystal is cut to so-called 29 degrees. That's detailed on this. And what you do now, that you have an 800 beam, and you will have something, a fluorescent beam, let's say 400. Now, if you do the math, and I cannot do it now because you have to make the inverse of this. If you do the math, 1 over 800 plus 1 over 400, that will give you the unknown frequency. So this will be your frequency generated. But this generated only at a certain angle. If you set your crystal at this angle, you can measure only, let's say, photons at 360 nanometers. And you can see the decay as you are changing the delay stage. If you want to measure the fluorescent decay at, let's say, 450, you have to rotate your BVO when phase matching will be fulfilled, phase matching criteria will be fulfilled. So that's why this is a slow process, because it can be done, of course we did it, just you won't have a whole spectrum from the very beginning. You have to make this spectrum one by one, 360, 370, 390, whatever. So this is not a nice thing. We did it also, but it's time consuming, of course. Okay guys, thank you. It was nice to